Hey guys, welcome to my lesson presentation. Today we're going to go over Module 4, Chapter 11, and we're going to talk about transformation, symmetries, and tilings. All right, so the first question we had was about rigid motion. So two boys were asked to reflect a pattern block figure shown on the right of the horizontal line through the center of the square. They rearranged the blocks to form the figure on the right. What type of rigid motion did they use? How would you help clear up their misunderstanding? So I'm going to move us over here. So we see on the right that we have our figure, and we see that we have our horizontal line in the middle. If we were to use rigid motion, we would move 90 degrees, and so that would be like a right angle. And so looking at what the two boys did, I think they had the right idea. They actually did 90 degrees twice. They did a full 180 turn rather than, which that is correct. They just didn't position it right. So doing the 90 degrees and then another 90 degrees, that should almost look like a mirror image. And we see right there, that's what it should have looked like after doing the 180 degree turn. So what I would recommend is to think about a horizontal line. I'm going to get my pen. To think about this right here being our horizontal line. And if we were to do a 90 degree turn, we would be right there. That's where our image would be. And then to do another turn, that's where our image would be. So they just didn't position it right. They turned the image correctly. The positioning of the image just was incorrect. All right, so now we're going to talk about symmetry. So we were asked to do three things. So we were supposed to identify one line of symmetry that has no rotational symmetry. We were to identify rotational symmetry, but no reflection symmetry. We were also supposed to identify one line of symmetry and rotational symmetry. So doing so, I have labeled these three things A, B, and C. Excuse me, just getting a drink. A, B, and C. And what we're going to do is we're going to use A, B, and C to label each image. And I have already provided the lines of symmetry for every shape and image. That way it'll help us, eliminate and do process of elimination. So looking at the first one, we see that that would be B because we see that we have no reflection symmetry. Otherwise, it would mirror the same image going down the x-axis. But we do have rotational symmetry. We see that the image is moved, and then that we see it does not reflect across the x-axis. Now for our diamond, we see that it would be C. It does have one line of symmetry and also rotational symmetry. I kind of call this like the thunderbolt, lightning bolt. This is B. It does have rotational symmetry, but no reflection symmetry. Otherwise, it would look exactly the same. And for the diamond, I actually thought that I was kind of in between C and, oh, goodness. No, I guess just C because it does have reflection symmetry, but that's kind of, we just want to specify what does not have reflection symmetry. But I wanted to point out that it does have reflection symmetry. But looking at our triangle, we see that that is A. It does have line of symmetry, but no rotational symmetry. This image is not moved. It's just the same. Down at the bottom, we see that is also A. It also has one line of symmetry, but no rotational symmetry. And we can also see that that also has a reflection symmetry as well, because it's the same over the other part of the axis. All right, so for a rectangle down here, we see that that is C. It has one line of symmetry and rotational symmetry. I kind of call this like our sideways triangle, but this is A because it does have one line of symmetry but no rotational symmetry. And our last one has at least one line of symmetry and rotational symmetry. So it's pretty easy. And so I actually wanted to go ahead and show all of these shapes with a 180-degree turn. I watched this off of a peer of mine, and I just thought it was interesting to do that. So we're going to go ahead and do that. So that image turned 180 degrees, looks exactly the same. This image turned 180 degrees. It looks exactly the same. This image as well does look exactly the same. And this image does not. The triangle does not, because it would almost be like a reflection symmetry axis. Rotating it 180 degrees makes that image a little different. So let's look at some more examples. Of course, our circle is going to look the same no matter what. And of course, our rectangle will as well. And then we see that our triangle, and I guess we could just notice, we can kind of just point out here, a triangle rotated, whether it's 90 degrees, 180 degrees, will not look the same. But when it's rotated 360 degrees all the way back to its starting point, it will look the same. So looking at our hexagon, we can tell that that looks the same as well. So it's just kind of fun to see those and see which ones, you know, would obviously look the same and which ones would not. So our next question, question number 3, was we were going to talk about vertex figures. So vertex figures were kind of like where all the shapes meet together. So our vertex would be the point where the blue, green, and pink meet in the middle. So we see, so what we're trying to do is trying to see if we were to do this pattern, if it would overlap or if it would constantly have a vertex figure. So we're going to remember that a full vertex figure has 360 degrees. So we're going to do this first. We're going to find our interior angles for each of these shapes. Sorry, my throat's just really dry. So our formula for that is n minus 2 times 180 divided by n. So our octagon has 8 sides, which I'm going to go ahead and say n equals the number of sides. So our octagon has 8 sides, so we're just going to plug that in. So 8 minus 2 times 180 divided by 8 equals 135 degrees. Our hexagon has 6 sides, so we're going to plug and chug that in as well. So 6 minus 2 times 180 divided by 8 is 120 degrees. Our pentagon has 5 sides, so 5 minus 2 times 180 divided by 5 is 108. And like I said, we're going to remember that a full vertex is 360 degrees. So what we're going to do here is we're going to add these 3 degrees up to see if we get 360. So adding up 135 plus 120 plus 108 will give us 363. And we see that that is more than 360 degrees. So, but that being said, we can go ahead and say that these shapes will eventually overlap. Even though they look like they may fit, they will eventually overlap each other. So I did a little visual with this image to show and represent these shapes overlapping each other. So we see that we had the green, blue, and pink, our octagon, hexagon, and pentagons, and we're just going to keep continuing the process that was once started. And we could see and we noticed that our greens are starting to overlap, and that our greens were overlapping our blues. So we see that from the image visually, and we see that from the numbers mathematically. So that's pretty fun. Question 3 was about tessellation. Was about if. Sorry, this was question 3, talking about vertex figures. So we were supposed to give an idea or give a response on what we could do to make these images fit together. And my response was tessellation. So instead of having these images overlap each other, what we'll do is we'll use tessellation, which is an arrangement of shapes closely fitted together, usually polygons, in a repeated pattern without gaps or overlapping, which is our goal. So using tessellation, we are going to point a vertex. We are going to click anywhere on here, and we will find a vertex of this image to the right. So that little white dot right there that I put in here, and I'm going to circle it so we could see it a little better. I'm gonna circle it in Y. So right here, we see that that is our vertex, and we see that we have 1, 2, 3 triangles, and we have 1, 2 squares. And I'm going to refer back to the previous slide. The vertex are where all the points of the shape meet together. So with that being said, we are going to use tessellations to see if this adds up to be 360 degrees rather than the images before. So we know that we have 3 triangles and 2 squares. And that must, since they're not overlapping each other, that must equal 360 degrees. Sorry. So our triangles must be 60 degrees and our squares must be 90 degrees. So we have 3 triangles, so we're going to multiply 3 times 60 will give us 180 degrees. And we're going to multiply our 2 squares by 90, and that'll also give us 180 degrees. And 180 plus 180 is 360 degrees. So we obviously see that that can work, and using tessellation is better than just guessing like this. All right. So we are going to demonstrate why triangle QPT is equal and congruent to triangle SPT. So I'm going to get my pen out. What color we'll see. I'm going to do purple because we can see it. So we're talking about angle QPT. And we're also talking about the angle, let me get another color. We're also talking about the angle SPT. And we see our little lines that we have here. We see that's a congruent line, that's a congruent line. These are congruent lines, and these are congruent lines. So what I'm going to go ahead and say here, these lines just represent that those two, we see that we have one line on both the P to Q and the P to S, because that means they are congruent to each other. So congruency means that they are the same shape, they have the same angle, they have the same degrees, they are ultimately just the same. And as well as the red lines, they have 2 lines, and the only reason why we put 2 lines is to differentiate from the 1 line. Like, this is a completely different angle. So we're going to say QPT is congruent to SPT because these are the same triangles, the same shapes, and we could see that when we outline this, they kind of mirror each other. Oops, sorry. They kind of mirror each other over the y-axis. So now we're going to do the next one. So the first one was they mirror each other over the y-axis. So we know that's correct. So we're going to demonstrate why angle QPT and angle SPT is true. We just went over that. Oh, angle. So this is the angle. I'm sorry, I'm just kind of confused myself. So the triangle is what we just went over. We're going to go over the angle now. So we see that these angles are congruent because we see that they are also on the same line. Q and S are on the same x-axis. It's the x-axis. This is the y. And we can see that if our 2 triangles were the same over the y-axis, we know they're going to be the same over the x-axis, meaning that these 2 points have the same angle. So we know that's correct as well. And we're wanting to demonstrate how or why angle QVP is a right angle. And I'm going to go ahead and do a little trick that I was taught in school. I'm going to draw a box right here because that kind of solidifies and states that that is a 90-degree angle. So so when you have the box like that, and you could see it because I drew it in for you. But this box is representing that angle is 90 degrees. And I'm going to go ahead and say that we could say PVS as well as QVP. This is a right angle as well, and it's also equals 90 degrees because they are congruent to each other. So we can go ahead and check that out as well. So it's pretty easy. Go ahead and get out of that. what we're going to do here, this is our question 5. Oops, let me go ahead and go back. We are going to construct a calculation of angle NOQ. And by doing so, we are going to label a couple of things first. So we see, first of all, we have our penta, which is P-E-N-T-A. And penta kind of stands for, penta obviously stands for pentagon. But the way I remember it is we say penta because we know penta has 5 sides. And let me click on my image. There's our penta, P-E-N-T-A. So there's our penta constructed. Now we're going to construct our triangle, which is PQR. Sorry, PQR. There's our triangle. And I did these colors because I think you can see them more clearly. And so what we're looking for here is we're looking for angle NOQ. So I actually watched a couple of my peers because I was late on doing this. And I did the one that I thought was kind of the funnest, was also that I also enjoyed a lot. I'm going to clear that. That I also enjoyed a lot. So I'm just going to explain it because there was multiple ways. There were a lot of multiple ways to do this problem. I'm just going to do it the way that I enjoyed best to do it. So we see we have the angle NOQ. And we see if we were to fill this circle with all of those same angles. Sorry, it's going to take me a minute. All right, and we're going to count those. 1, oops, get a pen. 1, 2, 3, 4, all the way to 15. Sorry, I just didn't want to fill all those in. Should have had them filled for you guys, but I'm going to go ahead and say that these angles, even though they may not look like I did my best, these angles are all going to be the same degrees as angle NOQ. So what we know is we have 15 of these angles, and we know that this circle equals 360 degrees. And so what I can take from that is that if we have 15 of these angles, we can divide by 360 degrees, and we can figure out what angle NOQ is, and for all these other angles. So they are 24 degrees per angle. So this is angle NOQ is 24 degrees. This is 24 degrees. And if we add that, if we were to multiply 24 times 15, that would give us, sorry, this looks a little funky, 360 degrees. So it's pretty easy. I really enjoyed that one for my peer, and I appreciate all their hard work. And you know, me using this visual just helped me a lot better, and I felt like it was easier to explain to you guys. All right, question 6. This one was fun, but also a little tricky. Trying to find a good place to move me. So I'm going to put me down here for a minute. So what we're going to do is we are going to find the height of the cliff. So our question was, what is the approximate height of the cliff? So first of all, we need to state what we know about this cliff. We know that this cliff, she uses 2 feet of ruler to measure, and that she has 1.5 inches apart marks throughout to the cliff, and she is 1/4 mile away from the cliff, and we are looking for the height of the cliff. And so what we're going to do here is we're going to do cross multiplication. So when I say cross, I mean we're going to go across and multiply this way. And some students may get confused and think that we're multiplying the numerators and then multiplying the denominators. But that's not the case. We are cross multiplying. But before we start doing that, we need to go ahead and convert a couple of things to make it easier on us to find the height of the cliff. So we know that 1.5 inches, and we're talking about this 1.5 inches apart marks. We know that 1.5 inches divided by 12 inches, and we use 12 because there's 12 inches in 1 foot. We're trying to convert everything to feet, so when we find the height of the cliff, we will get the answer in feet. So dividing that by 12, we would get 0.125 feet. And so we know 1/4 mile is 1,320 feet. And so what we're going to do now is we're going to cross multiply that. So we have our 1.5 inches, which is now 0.125 feet, times 1,320 feet, which was our quarter of a mile, the distance she was from the cliff. And so now we're going to multiply the 2 feet of ruler, which we're going to put 2, just, instead of saying 2 feet, we just know it's 2 feet, but it's 2 feet of ruler times the height, because we're looking for h. You could use x if you want to. I know a lot of teachers like to use x as the, solve the variable kind of thing, but I just use h because we can represent that by height. Let's put that there. So this is h. And so what we're going to do now is we're going to multiply everything. We're going to end up with 165 feet equals 2 times h. And to get rid of, what we want to do here is, once we get to this part, is we want to divide both sides by 2, because if we were to do that, we would get h by itself. So 165 divided by 2 is 82.5. So our height, or our h, will be 82.5 feet. Well, all right. Thank you, guys. That's all I have for today.